Okay, let's talk a little bit about nomenclature today. Nomenclature is just a fancy name for naming, and chemical naming is really important because if you know the name, then that will give you information about the chemical formula, and if you have a chemical formula, then you can give the correct chemical name. So there's a nice correlation there. Nomenclature is something that is developed and kind of kept track of by an overarching scientific body called IUPAC, which stands for the International Union for Pure and Applied Chemistry, and they come up with all the naming kind of rules. So today I want to talk a little bit about naming of ionic compounds. And remember that ionic compounds are a cation with an anion. So cations are positively charged and they're always metals. Of course, there's exceptions to that because it's chemistry, but in general, most of the time cations are metals and anions are nonmetals or groups of nonmetals. So when you have a metal that is chemically bonded to a nonmetal through electrostatic attraction because of this attraction between the positive and the negative, or if we wanted to think about it in terms of the periodic table, if we have something, here's our little stair step of metalloids, if we have something from the left-hand side of the periodic table that is paired with something on the right-hand side of the periodic table, then we have an ionic compound. And when we name those things, the naming is fairly straightforward. There's a couple different exceptions to rules, of course, but it's really just the name of the cation and the name of the anion. It's that simple and that complicated. The name of the cation is just the name of the metal. So if I have the sodium ion, for example, sodium is in column 1. It is it's an alkali metal. So it has a +1 charge when it loses that 1 valence electron. So the name of that cation is sodium. So, you know, the tricky part is I guess you have to know your chemical symbols, but you already do. If we have something like this, Al3+, then it's just the name of the metal. This is aluminum. Now the tricky part comes with the transition metals. So the transition metals are weird, and remember that the transition metals on the periodic table come in columns 3 through 12. So kind of this middle bit, and of course the inner transition metals fall in that too, this little island kind of down below. But especially in an introductory or general chemistry course, we usually don't spend a lot of time with the lanthanides and the actinides. So if we look in some of the more common metals up here, you know, we run into iron and nickel and copper and kind of the coinage metals. These guys are all called transition metals, and because of those kind of shifty d orbitals and the electrons in those highest energy levels, then they can have variable charges. So for example, iron can be iron 2+, or it can be iron 3+. And we need to be able to tell the difference between those two when we're naming things, because it could have a difference. It will make a difference in the way that it's going to react chemically. So this one's name is iron 2, and this is a Roman numeral 2 in parentheses, and this one is iron 3. Now back in the day, these used to have specific names that were kind of based on their Latin name, and so sometimes you'll see things like ferrous chloride or whatever, and that kind of refers to one of the specific ions. But for the current IUPAC standards, it is the name of the metal with the charge, if it's a variable charge, in parentheses. So that's going to be the name, that's going to be the way we distinguish between the two. So that's for metals, that's cations. For anions, it's the root of the name of the chemical element, which in this case is the nonmetal. So it's the root of the name of the nonmetal, and the ending is "ide." So anions are going to have the ending IDE, "ide." And now when we're thinking about anions, this is a pretty small portion of the periodic table. So we have our stair step of metalloids here. We're just talking about this kind of corner. And because noble gases don't like to make ions, right, they have a full valence already, then we kind of ignore them as well. So what we're really talking about is this small section of the periodic table between the metalloids and the noble gases. So you really only have to know the roots for this little triangle of the periodic table. So it's not that many, and it's actually pretty intuitive. At least I think it's more intuitive than some things in chemistry. So let's take nitrogen, for example. Nitrogen has 5 valence electrons, so when it picks up 3 valence electrons to get to a full octet, then we end up with a 3- charge. Nitrogen, the root becomes nit, right? So I took off the ogen ending on it, and then I'm going to end it with IDE. There's the nitride ion. Or let's take sulfur. Sulfur has 6 valence electrons. When I pick up those extra 2 to get to a full valence, because everyone wants to be a noble gas, then we end up with a -2 charge. So sulfur becomes sulf, and then we add the IDE ending, sulfide. Okay, let's think about one of the halogens. Let's take this guy. So bromine is a halogen. When it picks up an electron to have a full valence, then we have a -1 charge. This is bromine, so we take off the ene ending, keep the brome, and then we end it with IDE. It's the bromide ion. Okay, so we have the name of the cation, name of the anion. That's pretty straightforward. Then when we're naming chemical compounds, let's take our common example here, which you probably already knew the name of just because you've seen it before. This is table salt. The name of this guy is going to be the name of the cation, sodium. Name of the anion, chloride. And I know that I'm going to name it this way because it's a metal paired with a non-metal. So the sodium must have a +1 charge. The chloride must have a -1 charge. It's a 1-to-1 ratio because I don't have any subscripts that are telling me that there's any other way I need to balance these things out. Okay, it gets trickier again when we get into our different transition metals. So let's say we have, let's do this guy. So Cr is chromium, right? That prefix chrome means color. So different ions of chromium have different colors to them, which is kind of fun. So the different charges actually lead to different compounds, which have different colors in solution. So there's a little detective work that has to go on with ionic compounds because we have a piece of information here. Our fluorine, we know, is our fluoride ion. And we know that it's got a -1 charge because of where it is on the periodic table, right? Fluorine is one of our halogens. It just needs that extra electron to look like neon, to be isoelectronic with neon. This is saying that I have a 1-to-2 ratio, 1 chromium for every 2 fluorines. And if this guy has a -1 charge, then 2 of them have a -2 charge net. That means that my chromium, in order to balance that out, has to have a 2+ charge. With me on that? So when I name this thing, I have to name it in accordance because chromium is one of our transition metals. So it's here in the middle of the periodic table. It can have a variable charge. So when I name this thing, it's going to be chromium 2 fluoride. And remember with fluorine, it's UO, not OU. It's not fluoride, it's fluoride. Okay, now the other wrinkle to all of this, because I said of course it is this simple and this complicated, is that we also have groups of elements that have charges on them, and we call these polyatomic ions. And kind of what they are is right in the name, right? Polyatomic, many atoms that have a charge on them. Now, polyatomics are kind of wacky because there's a group of elements that is usually covalently bonded together that has a net charge on it, which is just kind of a weird thing, but we'll get into that in a little more detail as we talk about chemical structures in future videos. But for polyatomic ions, the naming of them, because that's what we're focusing on here, is the nomenclature. The naming of them is just that group of elements with that particular charge has a specific name to it. And so the name of the polyatomic is just the way that you'd name this. So for example, let's take this guy. SO4 with a 2- charge is called sulfate. And you might have heard, if not of sulfate, you might have heard of sulfite. Sulfites in things like red wine, they're used as preservatives. So you might have heard of people having sensitivity to sulfites. Sulfite is another polyatomic ion, but sulfate is one of the more common ones. The ending ATE or the ITE ending usually indicates that it ends with an oxygen, so you'll see a correlation there. So you'll want to know these polyatomic names, their associated chemical formulas, and the charge on them, because that's going to help when you're starting to put together some of these chemical compounds. So let's do some practice with some going from names to chemical formulas and going from chemical formulas to names. So let's start at the top here. Gold 1 phosphate. So that 1 in parentheses indicates the charge on my gold. So let's think about this. Gold is aurum, right? So Au, and it has a +1 charge. Phosphate, that 8 ending, indicates that it must be a polyatomic ion. And if I was to look up the chemical formula, or if I had it memorized, which I do, then PO4 has a 3- charge, and that is phosphate. When I have these two ions together, I need to put them together in such a way to where they make a neutral compound, because ionic compounds are neutral. So I need to have, when I add up the charges on both of these, I need to have kind of a net 0 charge. So that means I need 3 of these for every 1 of these. So when I write my chemical formula, 3 of these to 1 of these whole groups. That is gold 1 phosphate, and that's the way that you would read it. And if I read that in a paper, for example, I would know that that's the chemical formula, and vice versa. Now, zinc is kind of a weird one. Zinc is a transition metal. If we look at zinc on the periodic table, it is right here. There's a couple exceptions, of course, to the transition metal rule, that there are variable charges. So your teachers might want you to know some of the exceptions. 2 of the most common exceptions are zinc and silver. Zinc is always +2. Silver tends to be +1. There's been some papers published recently that show silver with different charges, but it will more often than not be a +1. The way that I remember this, just if you need a handy mnemonic here, is you know that aluminum is +3 because of where it is on the periodic table. 3 valence electrons, so that gives you a +3 charge when you lose them. +3, +2, +1. So if you kind of remember that, that'll give you your exceptions here. So zinc is 2+. Hydroxide is another polyatomic ion. The way that you can tell that's a polyatomic is you have the hydro, which of course is referring to hydrogen, ox, which is referring to the oxygen, and hydroxide has a -1 charge. So I have a 2+, I have a -1. When I put them together, they have to be balanced out. So that means I need a 1:2 ratio. If I have a polyatomic like this, and I am putting it into a chemical formula, and I need more than 1 of them, then I'm going to put it in parentheses with the number that I need on the outside as a subscript. So this means that I need 2 of my hydroxides for every 1 zinc. Now, again, you'll note that I've removed the charges once I put them into the chemical formula, because at this point, they are neutral. All right, let's play around with the next one. Copper. Copper 2. Copper is Cu from cuprous, and chloride is a halogen, so it's -1. So I need, again, 1 to 2, kind of like my zinc hydroxide here. Because chloride is just a monoatomic ion, so 1 atom with a charge on it, then I need 2 of those for every 1 of those, and that gives me the charge on my copper. Magnesium is in column 2. It's one of our alkaline earth metals, so magnesium has a 2+ charge. Phosphide, now let's kind of look at the difference between phosphate and phosphide. This "ide" ending, now that we're learning about naming, tells me that it's P3-. Okay? So with these guys, it's not as easy as just saying, well, I need 3 of these to 1 of these. I need a lowest common multiple. So that's going to be magnesium 3, phosphorus 2. Okay, so using that same kind of mentality, we can maybe play around with the other direction too.